Hello everybody, welcome to your first lecture in Physical Geology. This is your professor, Dr. Hurt, so glad you could be with me again today. We're going to be going over, like I said, this first lecture. Hopefully it'll just take, I hope it'll be around 40 minutes or so we'll see. I'll try to get through it as quickly as I can. So make sure that as you start off, you have your lecture assignment. You should have printed it out like this. I have mine here, and I'm going to be checking this, making sure, like, am I hitting everything that's on here, and answering all the questions. So just be aware that's what's going to be on there, and you should have that all ready for you. And I'm going to be keeping this over here, so if I keep looking over here, that's what I'm looking at. Anyway, so happy that you could be with me today. So we're actually going to go over today kind of an unusual topic. Maybe most science classes don't start off this way, but sorry, I'm making myself some coffee here. One thing I want to talk about, though, is what is science? And the reason that I want to talk about that is because I realized so many students come into this class and they don't really have such a great grasp on what science actually is. And I meet a lot of students who think that science is everything, and science can answer every question and can do anything, almost like it has godlike powers, and that's not really true. So I want to kind of give you maybe some context for understanding what science is. You know, where do you draw the box? Where are the boundaries? Where does science start and where does it end? So that's kind of the goal for you today, to understand what science actually is, where it starts and where it ends. Okay, because things sometimes they're defined by their boundaries, right? Anyway. We're going to be going along this just to kind of give you a little bit of background. I'm clicking along, just so you know who the heck I am, since you're going to be with me for next 4 months here. So like I said, my name's Professor Hurt, Sean Hurt, and here's my lovely family. I got my wife and 3 kids here, and there might be more coming. I don't know for sure. I'm not announcing anything, but Anyway, but I got this little guy. That's Frankie. That's the last one born. There's Teresa. She's 7, and there's Julia. She's 4 years old. And originally, I'm from Southern California, and I didn't want to go back to Southern California, and that's one reason why, because there's so much traffic there, and also that was a lot of reasons. But anyway, I'm one of these famous Californians that's come to Texas. So anyway, but I got my bachelor's degree from UCLA, University of California, Los Angeles, where I'm originally from LA, and did my PhD at University of Michigan. Very, very cold place. My wife was like, no, I don't want to. I wanted to settle down in Michigan, but she is like, no, I want to go somewhere warmer. So anyway, here we are, and it's hot enough for you. It's pretty warm here in South Texas. So anyway, my PhD is in Earth and Environmental Science from University of Michigan. So those are my credentials. But anyway, let's go on to this question of what is science. So one kind of first order thing of business I want to talk about is, we live in a cosmos and not a chaos. So that's the first question I say. Explain your own. What does it mean the natural world is a cosmos and not a chaos? So, these are both Greek words. Cosmos and chaos are both Greek words. So they have Greek roots. And the word cosmos, although probably when you think of cosmos, you think, outer space and all that. But it actually means something. It means outer space, but it means something different, not just outer space. Cosmos actually means something more like order or arrangement. So the fact that we live in a cosmos and not a chaos. What is a chaos? Well, you know what a chaos is. Chaos means there's just total disorder. Like if you go into my kids' rooms, after they've been playing, it's total chaos, right? There's no order, right? They've destroyed all the order. So you know what chaos means. But we don't live in a chaos. We actually live in a cosmos. It means that there's order to our universe, and you shouldn't take that for granted, because the whole fact that we can do science. We wouldn't be able to do it if we lived in a chaos, right? There's no science here in a chaos. I should use my little pen instead of the mouse. I don't know why I'm doing that. But there's no order, right? So there's no order here in a chaos, but there is order here. By the way, as we go through this course, you'll notice that when I write things on here, whoops. When I write things on here, it loves to like, let's see if it does it. Makes these, okay, see it's not doing it now because I'm trying to make it do it. But anyway, it makes these little spiky things, and I've had tech people come and try to figure out why it does that, and we can't figure it out, so whatever. Some bug in Microsoft Word, or Microsoft PowerPoint, I guess. But anyway, so you shouldn't take it for granted that we live in a cosmos, not a chaos, because we wouldn't be able to do science without that fact. Because we live in a cosmos, it means the natural world is ordered, it's rational, and it's intelligible. You have an intelligence, and that intelligence can be used to pick up on the intelligibility of the natural world. So we wouldn't be able to understand anything about the natural world or about nature if we weren't intelligent, and also if the universe was not intelligible. So don't take that for granted. It didn't have to be that way necessarily, right? So, but it is that way, and thank God, because now we can do science and have some kind of understanding of the natural world. So, sorry, I'm a total black coffee addict, so I have to have my coffee. But anyway, the natural world is governed by natural laws and principles. Okay, and that means that so there are laws, right? The law of gravity, laws of thermodynamics. It means that nature always obeys those laws. It never deviates from that. And because it never deviates and always follows those laws, it makes nature predictable. And thank goodness it's predictable, because wouldn't it be horrible if nature wasn't predictable? Wouldn't it be horrible if, sometimes when I drank my coffee, it, everything went right, and then sometimes it just turned into a dragon and flew away or whatever, right? So that would be terrible. But nature's predictable, right? And then it's predictable because it's rational, ordered, intelligible, and it follows certain laws. And a lot of the goal of science is to just figure out what those underlying laws are. So we want to understand, intelligence can understand the natural world. It means we can do science, and that means that we can try to figure out what those underlying laws of the universe are. What governs the natural world? How does the natural world work? That's basically what we're trying to do in science. The word science comes from a Latin word, scientia. And that scientia, what that means is knowledge. Now, it's not just normal knowledge. The word scientia, the Latin word scientia, knowledge, it was actually, there were two types of knowledge, or two words that kind of meant knowledge. There was scientia, and there's another thing called sapientia. Sapientia means wisdom, or maybe it means knowledge, but we could maybe translate it to wisdom. So there's knowledge of the natural world and kind of natural physical things. And then there's knowledge, but wisdom is not really knowledge of physical material things. It's more of knowledge of, think about people who are wise. What are people who are wise? What are they like? Do they know necessarily about how the natural world works? Do they know a lot of science? Not necessarily, but they know about things, maybe things of the heart, things of, family and life, and kind of those deeper things, right? That's what wise people know about. So it's a knowledge, but it's a different kind of knowledge. So a lot of people translate that wisdom. Scientia, though, science is not a wisdom, but it's a knowledge of the physical world. So what is science? So there are a lot of ways to define it, but this is the way I define it, and this is fine. So science is a methodical kind of reasoning that's ordered towards the discovery of truth about the physical universe, and it's based on observation. So there are a few key things I want you to understand here. First of all, it's methodical. So what does that mean that it is methodical? It means it follows a method, right? That's the scientific method. It's also about the truth, right? We are interested in the truth with a capital T, not subjective truth, but objective truth, things that are factual about the world and how the world works. And we're also interested in the physical universe, okay? So remember, scientia, knowledge, that kind of knowledge has to do with the physical world. So it doesn't have to do with things of the heart and the mind. It has to do with the physical world and how the physical world works. So that's what science is concerned with. It's concerned with the physical universe. And another thing here is it's based on observation. Now that's very important. Based on observation, we have a certain word for that I want to introduce to you. It's called empirical. So empirical means just that, based on observation. So you'll often hear something like the empirical sciences. That means they're the sciences that are based on data, the observations, right? So that's what we do in science. We make measurements, we do observations, and we try to learn how the world works from those observations. Okay, so it's based on observation. Okay. So that's answering number 3 to your question there on the lecture assignment. Okay. Now you might ask this. Okay, science is based on things that are observable of the natural physical world, things like matter, energy, time, space, things that exist in space. Okay, fill up space, and so time, matter, energy, space, those are all things science deals with. But you might ask the question, well, is that all there is? Is Dr. Hurt, isn't everything just atoms and energy and time and space? And the answer to that is, I guess that's an open question philosophy, but I think the stronger argument is no, that isn't all there is, right? There are other things. For example, there's mind, right? Mind is different than your brain. Of course, your brain is physical, but your mind isn't. Mathematical truths are true, right? That they're not linked, or they don't exist in a physical way, right? They are real. Mathematical truths are real, but they don't exist in a physical way. Things like logic, they're real, they exist, but they don't exist in a physical way. Some people believe in a soul or something like that, right? And it's just kind of hearkening to a fact that there's more than just atoms and energy and time and space. There's moral truths. There's truths of math, truths of logic, truths of reason. All these things that are not part of the physical universe. So those are all things that we don't study in science, right? We use math, we use logic, we use mind, but we don't study them. They're not the objects of our study. We study the natural world, things like minerals and planets and stars and things like that. That's what we're studying when we study science. Okay, so let's go on to. I'm sure you've heard the scientific method before. Just really quickly, we'll go through it, because there's some things, even though probably you've been hearing this since you were in elementary school, I noticed that a lot of people have mistaken ideas about the scientific method, so I want to kind of clarify a few things. One thing I want to especially harp on is, and I asked this on the test, both on the midterm and the final, is kind of making sure people are clear about the difference between hypotheses and predictions. So we'll go into that a little bit. So scientific method, you can break it up into different ways. I break it up into 5 steps. So first step is you make some observation of nature. You notice something interesting. Maybe, for example, you notice that every autumn the leaves fall off the tree. And now I guess that's sort of true here in South Texas, but I guess they do. Some trees do shed their leaves, but I'm sure fall colors and things like that, and the leaves lose their trees lose their leaves. So you might ask, that's interesting. I wonder why that happens, right? So science begins there. Scientific method begins there. Wonder why that happens. That's interesting. Wonder why that happens, okay? Number 2 is we propose an explanation for why it might happen. That's your hypothesis right there. So remember that a hypothesis, it's an explanation. We're trying to explain why something happens. Why? Okay, that's what we're trying to do with a hypothesis. And the reason I kind of make this big to do, because I noticed that a lot of people, they get it confused with a prediction. They say, I hear this a lot. They say, what do you hypothesize is going to happen? Well, that's not a hypothesis. That's actually a prediction. Hypothesis is trying to explain why something happens. Not what's going to happen. It's going to explain why it happens. We're trying to understand causal. One thing that if you want to recognize a hypothetical statement, so we're going to do this in the test. I'm going to give you different statements, and I want you to recognize the one that is a hypothesis, a hypothetical. Okay, so a hypothetical statement, a hypothesis, is often going to be causal. Remember that we're trying to explain why something happens. Well, if you're trying to explain why something happens, usually you're proposing a cause. So maybe the leaves fall off the trees every autumn because it gets cold. Okay, so that's a hypothesis. Okay, the trees lose their leaves because it gets cold. We're giving a cause. Okay, that's a hypothesis. Another hypothesis you could possibly suggest, if you think about this, is that it's not only the temperature that changes in the winter time, it's also the amount of daylight we get, right? So you know that the days get shorter during the autumn, during the winter, right? And so actually the trees might be responding to daylight changes, right? So that's another hypothesis. So there's could be one or both of those could be true, or neither of them could be true. So to go forward, what we're going to do is we're going to try to come up with an experiment to test which hypothesis is true. So that means that we're going to have to make a prediction off of our hypotheses, okay? So that's where we're going to try to guess what's going to happen. And usually what a prediction is we're trying to guess what would happen if the hypothesis is true, okay? What's going to happen, predict what's going to happen if hypothesis 1 is true or if hypothesis 2 is true. So often predictive statements are actually, should be if-then statements. You know, if hypothesis 1 is true, if trees lose their leaves in the fall because it gets cold, then a tree kept in the warm greenhouse over the winter will not lose its leaves, right? So we're going to control the temperature. We're going to see if it loses its leaves or not. That would be a controlled experiment, and that would test our hypothesis number 1. Okay, but it would also test hypothesis number 2, because we could see if we keep it in a greenhouse, it's still going to be exposed to those changing light levels, right? So we'll see if that has something to do with it. All right, now the fourth part is just to test your prediction, just see what happens, actually do the experiment. And after that, we're going to make, that's actually observation. Remember, science is all based off of observation. So we're going to actually observe nature and see if it behaves according to our hypothesis or if it does not. So we carry out the experiment, we grow our plants inside of a greenhouse, and then we analyze our results and see if they match our prediction or if they don't match our prediction. So if it matches our prediction, it will corroborate our hypothesis and we'll accept our hypothesis. If it doesn't, we'll have to go back and reassess our hypotheses, okay? Now, hypotheses are just kind of like, you can think of them as just kind of good guesses. Once there's enough data to back up a hypothesis, we no longer call it a hypothesis. Then it becomes a law or a theory, okay? So once something has a tremendous amount of data supporting it, it will become a law. Once it has some evidence supporting it, or a good amount of evidence supporting it, we can raise it up to a theory. So we start off with, everything starts off as a hypothesis, and it moves up the ladder of certitude to a theory, and then to a law. Okay, and then as we have a law, then we become very certain that this hypothesis is correct, or this idea is correct. Okay, so again, I know this is a lot of writing on here. I usually don't like to make these kind of slides with a lot of writing, but a hypothesis, I just want to clarify this because this is on the test, like I keep saying. I make you tell the difference between hypotheses and predictions. A hypothesis is causal. So the leaves fall off the trees because it gets cold, right? A prediction, though, is not going to be like that. So in a prediction, we're just trying to guess at what's going to happen. Okay, we're guessing at what is going to happen based on our hypothesis. Okay, so they're often if-then statements. If hypothesis 1 is true, then we expect that the leaves will fall off the tree if it gets cold. Okay, so that's how it all works. Another couple things I want to talk about here. So I'm looking now at our What is Science Lecture 1 assignment. So describe the difference, it says, number 5, describe the difference between a quantitative and a qualitative observation. Okay, so I did want to talk a little bit about that because, everything that we're interested in, science, we're interested in observations because science is empirical. It's based on observation. So we do kind of divide up different observations. We have qualitative observations and we have quantitative observations. Qualitative means that they're focused on qualities. Things like shape, color, form, things that cannot easily be measured. Okay, so there's a lot of things that we can observe, we can see, but we can't necessarily measure it or assign a number to it. Okay, so I'm sure there's a lot of things that you can think of that you observe that you can't really measure per se, right? So some things like that, like I said, the shape of things, the color, the form of it, right? Those are all things that are qualitative. Quantitative observations, on the other hand, are highly preferred in science. We're trying usually to quantify everything because we want to be precise in our observations. So those are things that involve measurement. So once you get measurement, then you're in the realm of quantitative. Quantitative means quantities. We're measuring and counting quantities of whatever it is. Okay, so that's the difference between those two. So you should be familiar with that on the test too, because that's another possible test question. Okay, so just to kind of get you to start thinking about quantities. So what are some things that can be quantified in this world? What are some things that you could quantify? So now we're still on number 5, but you answered number 5, but this is kind of just extra, but we'll talk more about this when we get to the metric system in the next lecture. So it's just kind of interesting. I find this fascinating, but there's actually only 7 independent dimensions of the universe that can be measured. So if I ask you, what are some things you could measure? You probably think of things like maybe speed, maybe time or temperature, weight, things like that. But there's actually only 7 that can be independently measured. You'll find that everything else breaks down to some combination of these 7. So those 7 things are distance, time, mass, temperature, electrical charge, amount of a substance, and luminosity. Probably most of those things, luminosity is a little bit weird. Luminosity is how bright something is, okay, how much light it gives off. Notice there's nothing like speed here or velocity, right? And the reason is because remember that speed is just a distance over a time. Okay, like I said, that's speed, right? So speed is a dependent dimension. It depends on distance and time, and distance and time are both independent dimensions, right? So everything that you can measure besides these 7 breaks down into some combination of these 7. It's really interesting. I just find it fascinating. There's just these 7. What's so special at the number 7? I don't know, but it's just a kind of a funny little thing about our universe. So anyway, what does it mean that dimensions are independent, right? So you might think about something like volume or density, right? Well, volume is just a distance in three directions, right? Height, length, width. That's a volume, right? So that's again, it's based on 3 independent variables. Okay, density. Think about density. Just breaks down to a mass divided by a volume. Okay, so again, those are all dependent. They depend on different dimensions, these different independent dimensions. Okay, so all those things break down into some combination of those 7 independent dimensions of the universe. So we'll talk more about that. I kind of want to introduce that right now. I know that there's not a lecture assignment question about it, but I just kind of want to get you familiar with the idea because there'll be questions about it. I'll ask more about it in the next lecture assignment. We talk about the metric system. Okay. So now let's talk about, I kind of started off this whole lecture saying I kind of want to give you some boundaries for understanding what science actually is, where it starts, where it ends, right? Because science isn't everything. It doesn't explain everything. It can't explore everything. It can explore certain subjects, and other subjects it's totally blind to. Okay, so let's talk about where science starts, where it ends. Okay, so now we're going to start talking about number 6, right? So number 6 on your lecture assignment. And it says, I want you to try to think of a question that is impossible to answer with science. Doesn't mean that we can't do it right now because of technological limitations, but it's the nature of the question is impossible to answer with science. Okay, we can't answer it with science. So let's talk about some things, some aspects of a question that make it either possible or impossible to answer via science. Okay. First of all, remember that science, so 3 things, we could add more to this, but there are 3 things we could talk about here. So those 3 things we're going to talk about are every scientific question has to be about something observable, it has to be something falsifiable, and it has to be reproducible. Okay, we'll talk about each of these 3 in turn. Okay, so first of all, let's talk about the hardest one for students to usually to understand. That's falsifiability, aka refutability. So falsifiability, refutability, it's the capacity for a statement, theory, hypothesis, whatever, some scientific statement, to be contradicted by evidence. Evidence. So evidence is, again, physical observations. That's what evidence is. Okay, evidence is physical observations, things that are evident, things that you can see. Okay, for example, the statement "all swans are white." That's a scientific, it's a statement that could be assessed by science. We can falsify that, or we can refute it, because we can go and try to observe to see if there are such things as black swans or red swans or pink swans or whatever. Okay, so we can actually go and try to prove that it's true or try to prove that it's false by observation. Okay, so that statement happens to be false because there are black swans. There's actually, in Australia, there's actually a species of black swans. So it doesn't matter if it happens to be false or happens to be true. That's not the question. The question is, can we prove it true or can we refute it via observation? Okay, that's what falsifiability and refutability have to do with. Now, you might be asking, well, what on earth is it then that is not falsifiable by evidence? I'll give you some examples. Imagine this. This is kind of a silly example, but imagine this. Let's say there was a scientist who wanted to verify his hypothesis that most bachelors are unmarried. Okay? Does that make sense? He wants to go out and do a scientific study and observe if most bachelors are unmarried. Make sense? Of course, it's silly. It doesn't make any sense. Why doesn't it make any sense? Because what it means to be a bachelor, it means that you are not married. You're a male who is not married. Right? That's the definition. That's the meaning of the word. Well, one thing about science is that science is totally blind to meaning. Science can't tell you the meaning of a word. So that's the subject of philosophy, not science. Science can't tell you the meaning of a word. So to do a study like that, where it's part of the definition of bachelor, makes no sense. Okay, so you can't falsify that with evidence. It's true or false based on logic, not based on evidence. Okay, so that doesn't make any sense at all. Be careful with this. A lot of students get confused about falsifiability. Falsifiability, there's a difference between something being false and something being falsifiable. Falsifiable just means it can be proven false or true via evidence. It doesn't mean it's false. Okay, so there's a difference there. I have some students, sometimes I'll ask them, think of something that's falsifiable, and they'll say, how about this? The sky is blue. The sky is blue, so therefore it can't be proven false, so it's not falsifiable. Does that make sense? No, that doesn't make any sense. The fact that the sky is blue and doesn't change its color, can't be proven false, doesn't mean it's not falsifiable. It just means that the sky is blue. That statement can be proven false or be proven true via evidence. So it is falsifiable. It's just not false, if that makes sense. So I hope that's clear as mud. But again, the basic premise here is that you can prove, in order for something to be falsifiable, a statement to be falsifiable, you can prove it true or prove it false via physical evidence. So hopefully that makes sense to you. So there's a difference between false and falsifiable. Okay, falsifiable means something could theoretically be proven false by evidence. All right, so that's falsifiable. A good example of something that is not falsifiable and not science is math. Mathematical truths cannot be falsified by evidence. The truths of math are based more on something like logic. Okay, it's not based on physical observation. Okay, so some things, for example, there are some things in nature that follow mathematical principles, and there's some things that don't. Okay, for example, if you walk a mile and then you walk another mile, you walk 2 miles total, right? You walk a mile, you walk another mile, you walk 2 miles total. That's an additive rule. It follows an additive principle in mathematics. However, if you take a cup of salt and mix it with 1 cup of water, you're not going to get 2 cups, right? You're going to get something else, because the salt's going to dissolve into the water. You'll get a cup and some amount of something else, right? Some salt sludge, but you're not going to have 2 cups total. So that does not follow a mathematical additive rule. So nature does not follow math in every single thing, right? So that doesn't disprove math. It just means that nature doesn't follow mathematical principles, if that makes sense. So anyway, if that's confusing to you, it's okay. But I'm just trying to give you examples of things that are not science, and because they are not falsifiable by physical evidence. Okay, another thing is reproducibility. Reproducibility means that not only do you have to make your observations, but other people need to be able to generally make the same observations as well. So people need to be able to reproduce your observations, reproduce your experiments. So it simply means that other people can make the same observations, and they can make the same experiments, and they can get the same results and repeat your experiments. So if things are not reproducible, they can't be reproduced, we don't consider that science. Something that you could kind of think about, we have a whole history of history, right? History are single one-time events that have happened through history, right? So we don't study that with science, right? We don't do a scientific study of history because they consists of one-time events that occurred throughout human history, right? So they're not the subject of science because they're not reproducible, right? We can't go and reproduce Washington crossing the Delaware River or something like that, right? So that's an example. I know that some of this stuff is like obvious, but it needs to be studied because a lot of people nowadays, they don't understand exactly where science starts and where it ends. So anyway, third thing here is that like I keep saying, science is observable. It has to be based on observation. You have to be able to observe. So that's the third thing, that it has to be physical and observable, something that you can see, smell, touch, feel, or it can be detected somehow with some instrument, but it needs to be something that is observed in the physical world. Okay, just some examples, because you have number 6 and number 7. Those are kind of the most difficult questions on your lecture assignment. So you have to give me an example of something that is impossible to study scientifically. Ignore technological limitations. Like some students will say, like, what color is a planet 34 million light years away? We can't tell because we can never look that far. That's a technological limitation. I'm talking about things that just are impossible to answer with science. So let me give you some examples. Science, not science, okay? What parts of the brain are active when someone is in love, okay? We can study that with science, but how you feel when you're in love, how you feel when your boyfriend or girlfriend walks into the room, or your wife or husband or whatever, that's not something that we can study with science. That's a subjective feeling. We can't study that with science. We can look at your brain and see what parts of your brain are lighting up, but that doesn't tell us anything about how you feel about it, right? So emotions are not science. Just asking the question, what is love? That's an important question, right? You want to have some understanding. What is love? What's the meaning of life? There's so many questions you could ask, that are important, but you cannot answer those with science because they're questions about meaning. Science can't answer questions about what words mean or what certain concepts mean, right? It can tell you about certain aspects. There's a lot of scientific facts that are pressed upon those questions, but it doesn't actually tell you what something means. Like I said, I gave the example of Washington crossing the Delaware River, right? You can't. Those are singular, one-time historical events. It can't tell you. We can't tell you exactly about historical events because they're single, one-time things. They're not reproducible. However, what is the average discharge of the Delaware River? That's something that we can measure and we can reproduce and get different answers. Anybody can go to the Delaware River and measure its discharge per year, right? So those are things that are science. Here's another example. Science. What is the surface area of the Earth? Measuring the surface area of the Earth. We can do that. But when it comes to something like mathematical truths, like what is 1 + 1 equal? Science can't tell you that, right? Science can't tell you. You can't prove scientifically what 1 + 1 equals. Okay, that's a mathematical truth. It's not a truth about the physical world. Some things, maybe even a lot of things in nature, follow mathematical principles, but the mathematical principles don't come from the scientific observation, if that makes sense. Okay, it's an important distinction. All right, so that's what is science. Okay, so I hope that now you have some background on what is science. So now you've finished. You've got your lecture assignment. You finished up to number 7, number 8. I hope you get number 8. Number 8 is kind of my. Okay, this is kind of the whole point. Is it possible for science to answer every question? Hopefully, you know the answer to that now. I was so pleased because on the final exam, nobody got that question wrong. Because I'm always harping on it. Because I don't want people to leave the class thinking that science, it answers everything, it knows everything. That's not true. That's simply not true. So anyway, we already talked about number 9, so you finished that. Now we're going to talk and we're going to finish up here really quick. So I told you what science is. I want you now to have some understanding what geology is, because we're studying now physical geology. So we're going to talk a little bit about what different things that geoscientists study, and then what are some important contributions that we geoscientists make to society. Okay, so kind of things that are helpful to a society. Okay, so what's physical geology? There's a beautiful picture of the Grand Canyon there, right? So we study all sorts of things: rocks, minerals, earthquakes, fossils, volcanoes, just to name a few. There's more. I mean, you see that we have 25 lectures in this class, and most of them are on different things. Okay, so a lot of things that we study. We're going to study streams, and we're going to study the core and the mantle and the structure of the Earth. We're going to study glaciers. We're going to study groundwater and surface water and so many things. So all those are all things, sediments, soils. Those are all things that geologists study. Okay, so anyway, that's a little breakdown to you. You can pick any one of those things for number 10, and much more. Right, so we study much more than this. Okay. All right. So why study geology? What are the contributions that geologists make to society? Okay, so I give you so many examples here, but one of the main ones is natural resources, right? So if you look around you right now, you look at your device or your screen or whatever, you look around. I'm looking around myself right now. There's so many things that ultimately come from geologists, right? So from different mineral petroleum resources. Okay, so for example, here are some common ores that we mine, minerals that we mine in order to get different metals. Aluminum comes from a mineral bauxite. Copper comes from a mineral chalcocite. Iron and steel come from a mineral called hematite. Lead comes from a mineral called galena. Okay, so natural resources, that's one thing that you could put for number 11, natural resources. Okay, and then explain a little bit about what do you mean by that? Well, it's all the different things that we need for everyday life here, right? You need aluminum, copper, iron, steel, lead. If probably all of you are going to use some petroleum product today. You drive around your car, and if you didn't, then you're going to use some product that got to your store by a petroleum product, right? So petroleum, gasoline, natural gas, fossil fuels, coal, people use that every day, right? So that's all part of natural resources, okay? If you have a smartphone, I'm sure almost everybody has a smartphone, but if you have a smartphone, so you have your phone, it's amazing that in a phone, there's all of those different periodic elements, elements of the periodic table in there. So look at how many of them, and probably a lot of them are really weird, right? Indium. Have you ever heard of indium? It's an element, right? Indium, tin, oxygen, aluminum, silicon, potassium. Here's some really weird ones. These are the things that are known as rare earth elements. They're kind of it's a very political thing because China controls about 50% of the rare earth element resources in the world. Okay, and so it's kind of a thing. It gives them a lot of power, right? So yttrium, lanthanum, tiberium, praseodymium, europium, dysprosium, gadolinium. I mean, there's all these weird elements probably most of you probably haven't heard of, right? So those are all in your phone, right? And geologists have to find all that stuff. So that's all part of natural resources. So let's look how many are in there. It's amazing. Another thing that geologists work on is the environment, right? So of course, one hand we're taking things from the earth. On the other hand, we're trying to protect the earth and conserve its resources and for future generations as well, right? So geologists do both, right? They got to take the natural resources, but they also have to conserve and preserve the natural resources and protect the environment as much as possible too. So just some examples. Here's just some examples of big environmental issues that geologists work on. Hydraulic fracking, you probably heard of that. Hydraulic fracking is what the gasoline, natural gas industry uses to extract crude oil and natural gases from Earth, right? It's a very contentious, controversial issue. So that's something that worries a lot of people. Geologists are heavily involved in that. Melting, glaciers melting from climate change, things like that. Geologists are very heavily involved in things like that. Mine remediation. So what do you do after you use up all of the minerals from a mine? A lot of times there's very toxic materials left over. So geologists are heavily involved in that too. So, geology, if you're interested in a career in geology, we're not only just taking resources, which is important. You need those resources, but we're also trying to protect the environment as well. So, these are all big issues that need people to work on them. So, it's a very rapidly growing field that you might be interested in, right? Radioactive waste storage. This is so fascinating. We're 20% of our energy in America comes from nuclear energy. Where does all that nuclear fuel, all that spent uranium, highly radioactive uranium go? Highly dangerous, highly toxic uranium go? Goes right now into the Yucca Mountain Radioactive Waste Storage Facility. It's a very deep underground mine, very, very deep mine. And that's where we put it all. And we kind of hope that things are going to work out there. So, but anyway, the big issues, and we need people to work on them. Another big issue, this is the final thing you can put for number 11, or mitigating natural disasters, So geologists are heavily involved in that as well. Think about natural disasters. 2011, probably some of you can remember this, 2011, 10 years ago, we had the great 11 years ago now, the great Japanese tsunami destroyed the Fukushima power plant, right? Created it's a natural disaster, wiped out this nuclear power facility, right? So very, very, very dangerous, right? That tsunami killed something like 10,000 people, but it could have killed 1 million people. The tsunamis are highly dangerous. The 2004 Indonesian tsunami killed, upwards of 200,000 people. Tremendously dangerous, tremendously tragic loss of life. The reason that this Japanese tsunami didn't kill a million people or hundreds of thousands of people, easily could have done that. The reason that it didn't do that is because geologists, seismologists have been working around the clock to try to come up with ways of predicting natural hazards. So, it saves lives as well, saves a lot of lives. Volcanoes, predicting when volcanoes are going to erupt, giving people fair warning, trying to give a good assessment of seismic hazards in different areas. Those are all very, very important things that geologists do. So anyway, I've gone on for 45 minutes. Hope you've enjoyed this first lecture. If you found it a little bit of dry, hang in there, because things I think get more interesting as we go forward. We have to talk about the metric system next lecture, which is a little bit dry too. But after that, we're going to start getting into kind of what I find more interesting stuff. This is important, but I think not as interesting to me. But we're gonna start getting into rocks and minerals soon, and earth structure. So anyway, hang in there, and I will talk to you next time. Don't forget, we're going to have an online class. If you have any questions about this lecture assignments, please join the online class. That's when we're going to talk about all that stuff. So anyway, hope you have a good week, and just let me know if you have any questions at all. I'm here to help you. Bye-bye now.